Okay, so now I'd like to go through a good example of a problem in one-dimensional kinematics. And the problem statement is this. Think about the kinematics involved in an aircraft landing on an aircraft carrier. Okay, so the problem statement isn't something like, oh yes, the initial velocity of the aircraft was 68 meters per second, and the length of the aircraft carrier was 120 meters. How long did it take to come to rest, and so on? Physicists don't care about problems like that. They don't care about, particular problems. What they care about is understanding everything that is possible to know about that kind of situation. Aircrafts landing on an aircraft carrier, for instance. What's the basic kinematics physics involved? Okay, so here is the, let's just do an example. Example, e.g. Okay, very good. So aircraft landing on an aircraft carrier. So the first step in solving a physics problem is to draw a good diagram. Okay, so what we've got is there's water. And we've got an aircraft carrier, so it's a ship on the water. Okay, and so this is the captain in here. Okay, and what does the captain look like? He's got a captain's hat. Okay, there's the, whatever. And the idea is we've got an aircraft coming in here, so it'll be coming in like this, and so this is the aircraft. So it might look something like this, and there's the cockpit, and there's the wings, and there's the tail, and so on. There's your aircraft coming in. And then so the idea is it's coming in for a landing, and so at this point, at the end of the deck of the aircraft carrier, it's going to be coming in with some initial velocity, v initial, moving to the right. And what we want to do is we want it to stop before it hits the end of the runway. And so we might take, the x-axis is along here, and we will take this as x equals 0. So x initial is equal to 0, and x final is equal to L. Okay, so we have an initial velocity, vi, and we have the length of the runway on the aircraft carrier is L, and we want the final velocity at this point, v final, to equal 0. Okay, and there are various parameters in this problem. So we have initial velocity, we have final velocity, which we've specified to be 0. We have the displacement, delta x, is equal to x final minus x initial is L, is the length of the the runway. And we also have other things. So we might be interested in, say, for instance, the acceleration required. So we say the acceleration. We will, for simplicity, obviously the acceleration is going to be negative. Okay, it's going to need to be decelerating, so to speak, a negative acceleration, velocity in this direction, acceleration in this direction. The aircraft slows down from a high initial velocity to 0, and we will assume that it's constant. Because if we don't assume it's constant, then we have to involve calculus. Okay, so we'll assume it's constant just for simplicity. Okay? Another thing we might be interested in knowing about, or a parameter that's involved in this problem, is the time. What is the time interval? What is delta t? Okay? And so there's a whole bunch of variables in this problem. The initial, v final, delta x, delta t, the acceleration, and so on. And so we might think to ourselves, of all of these variables, what should we take as known variables and what should we take as unknown? The first thing I want to stress is this is a one-dimensional problem in kinematics. There are only 2 kinematical formulas. There aren't 5 independent kinematical formulas. There's only 2, which means you can only solve for 2 unknowns. So out of all of these variables, you need to pick which ones do you think would be unknown and which ones and then the rest should be known. Okay, so it's easy to sort of estimate what the initial velocity is. So let's assume that's known. The final velocity, we know that to be 0. We want that to be 0. Let's also suppose that the length of the aircraft carrier deck is known. Okay, so these here then would be known. And that leaves us 2 variables in the problem. The acceleration the constant negative acceleration required, and the time that it would take to bring the aircraft to rest. So these two would be unknowns. So these are two unknowns. Let's choose those to be our unknowns, because these are easy to measure. These are harder to measure. And so given these, we'll figure out what these are. Okay? So that's the sort of thing. So the first thing you do is you draw some kind of a diagram illustrating the physical situation. The next thing you want to do is you want to make sketches of position versus time, velocity versus time, and acceleration versus time graphs. Okay, and you want to include on those graphs, you want to carefully label those graphs with all of the variables that we have up here. Some are known and some are unknown. Okay, so this is position. We'll draw them kind of smaller. Position versus time. And we're going to start at, say, t equals 0. And we're going to go for an unknown amount of time, delta t. That's how long it takes the aircraft to come to rest. That's one of our unknowns. And we're going to say, okay, the initial position, x initial, is 0. We know that. And x final is up here. X final is equal to L, the known length. We're going to assume we know that, or we can estimate that reasonably. Okay, so we have that. So we know at t equals 0, the aircraft is at x initial equals 0. And at t equals delta t, we know the aircraft is at x final equals L. So we have these 2 points on a position versus time graph. And now we need to sort of connect these dots. And of course, if we connect these dots with a straight line, well, that corresponds to a constant velocity. Well, we certainly don't want that. Okay, so what we want is the velocity to start out high, at a high positive value, v initial. So remember that the velocity at any instant of time is the slope of the position versus time graph. So the initial slope of the position versus time graph, I draw that as a straight line at some angle, a little triangle like that, indicating a slope, an initial slope of v initial, initial positive slope of v initial. And we know that the final slope of this position versus time is the final velocity, and that's 0. So the final velocity has 0 slope. So v final is equal to 0, and v initial is some large positive value. And so now we need to connect this dot to this dot with a smooth curve that starts with this slope and ends with this slope. And we're also assuming constant acceleration, which means that velocities change linearly with time and positions change quadratically with time. So it's a parabola. It's a parabola that has 0 slope here and some positive slope there, and so we just draw a nice parabola like that which connects those two. Okay? And that is a very accurate representation in our minds of the position versus time. So we can read off of this graph immediately. We can see that say during the first half of the time, the aircraft has covered more than half of the distance to L. So in the first half of the time, it's here, because in the first half of the time, it's moving faster than in the second half of the time. Okay, so you can just read off of the graph some basic physics, some basic kinematics of what's happening. Okay, so we got that. Very good. So now let's draw the velocity versus time graph. So that's velocity versus time. So we're starting at t equals 0, the initial time. The velocity is some large positive value, v initial. So we're up here. And then after an amount of time, an unknown amount of time, delta t, has elapsed, the velocity has been brought down to 0. So we have these 2 points on our velocity versus time graph. And then we ask, well, how do we connect those 2 points? Well, again, we're assuming, for simplicity, okay, keeping this as simple as possible, constant acceleration, which means that velocity versus time graphs are straight lines. Velocity changes linearly with time, and so it is, in this case, just a straight line. And the slope of this straight line, draw a little triangle like this, the slope of that straight line is the acceleration. We're assuming the acceleration is constant, and so that's right, velocity versus time graph is a straight line. And the acceleration is negative, this constant is negative, and you can see that. The slope of that graph is some constant negative value. Its velocity decreases linearly to 0 under constant negative acceleration this way, you know, due to the braking mechanism and so on, and the reverse thrusters on the aircraft, etc., etc. Okay, so very good. And then the third thing we want to do is draw the acceleration versus time graph. Okay, so this one's really easy. This is 0 to delta t final. The whole time, oh, should have drawn that as acceleration is negative, so let's put it here. Let's put the time axis up here. This is 0 acceleration, and so between time 0 and time delta t, the aircraft is suffering constant negative acceleration. So it just looks like that. So there's some constant value of a which is negative below 0. Okay, so this is acceleration versus time, velocity versus time, position versus time. And what else? That's it. Okay, so now we have a pretty clear picture in our minds of the kinematics already. Okay, and you can think about derivatives. If I take position versus time, the instantaneous slope is large, and then it steadily decreases. Okay, that should give us the velocity versus time graph, and it does. Okay, the slope of the instantaneous slope of the velocity versus time is the instantaneous acceleration. While at every instant of time, it's the same slope. It's the same negative slope, and so on. So just check your graphs, see if everything makes sense. Okay, then the next thing to do is to write down some kinematical formulas. Now what you could do, you're looking for an acceleration, you're looking for a delta t, and what you might want to do, what you might be in the habit of doing, is looking at these 5 kinematical formulas, hunting around and trying to figure out which formula would be most convenient to use. Okay? So that's not how I would encourage you to solve kinematical problems. I would encourage you to write down the 2 basic kinematical formulas, specialize them to the case of constant acceleration, and then write down those 2 kinematical formulas for the case at hand. You'll end up with 2 equations. Okay, and then you solve those 2 equations for these 2 unknowns. The variables that you've decided are unknown. Okay, this is a foolproof method of solving any kinematical problem. Just write down the 2 basic kinematical formulas. Okay, so the first kinematical formula basically follows from the definition of velocity as dx dt, as the instantaneous slope of the position versus time graph. Okay, and so when you integrate that equation, you get this general kinematical formula that the finite displacement over the time delta t is equal to the average velocity times the time interval delta t. This formula is completely general, and then you say, but I'm assuming the acceleration is constant. That super simple case that I don't have to use calculus. Okay, so then what I can do is, well, if I know the acceleration is constant, that means the velocity is linear in time. This is v final is equal to 0. The velocity varies linearly with time, and I know that the average velocity is just initial plus final divided by 2, halfway in between those 2. So the average velocity is 1/2 the initial plus the final, okay, times delta t. Okay, so I have that. And that delta x on the left-hand side is x final minus x initial. Okay, and x final minus x initial is my L. Okay, so I look at, and I also know that v final is equal to 0. Okay, so I write down the general formula, I specialize it to the case of constant acceleration, and then I start plugging in known values. V final is 0, and x final minus x initial is equal to L, and so what I end up with is this equals 1/2 the initial delta t, and so I can just write that out. So that says that the length L of the aircraft carrier deck is equal to 1/2 v initial delta t. Okay, and so that is one equation. You have only 2 kinematical formulas. One of them tells you that it's the relationship between the length of the deck L, the initial velocity, and the time interval delta t. Then this is a foolproof method. Then you just write down the second general kinematical formula, which follows from the definition of acceleration as the time rate of change of the velocity. Okay, and so then the finite change in the velocity, v final minus v initial, is the average acceleration times delta t. This formula is always true. In the special case of constant acceleration, the average acceleration, well, is just that constant acceleration a. Okay, and so that just becomes a delta t. Okay, so now I have delta V is equal to A delta T. My second kinematical formula is specialized for the case of constant acceleration. And then I start plugging in values here. So this delta V, that means change in velocity, V final minus V initial. I know that V final is equal to 0. Okay, so that drops out. And so I'm left with this equation. I'm left with, and I want to write this as, V initial is equal to, bringing the negative side to the other side, negative A delta T. And that's my second formula. There are only two independent kinematical formulas. These are the two equations they generate. The second equation is a relationship between the initial velocity, the acceleration, and delta t. And by the way, the acceleration is negative, so negative a is a positive number, which is right, because the initial is a positive number. Okay, so we have that. And then we look at those two equations, and we try to solve those two equations for these two unknowns, a and delta t. Okay, so there's an a. And you'll notice that both of these equations are, in this case, proportional to delta t. They contain a delta t. So both of those equations can be solved for delta t. Let's look at that first equation and solve for delta t. The first equation says we're going to eliminate delta t by solving both equations for delta t and equating that. So delta t is equal to 2L divided by VI. Great. But delta t, according to the second equation, is negative VI over A. Okay, so this equals this. What am I trying to solve for again? A. I've eliminated delta t, the other unknown. So I just solved this equation for A. So this tells me that the acceleration A is equal to negative VI squared over 2L. Okay, so that is an important result. I think this guy's running out a little bit. Okay, so that's great. So are you done? No. Now you have to check this answer. This is how especially your long answer problems are like this. They're just algebraic, and that's your answer. Now you need to check that answer, and there's multiple ways that you check that answer. The first way that you check that answer is dimensional analysis. You say, on the left-hand side, we have the dimensions of acceleration, which is length over time squared. On the right-hand side, we have the negative sign has no dimensions, neither does the factor of 2. We have a velocity squared. Okay, so that is equal to, question mark, a velocity squared is a length squared over time squared, divided by a length, so 1 over length. That length cancels. So I have a length over time squared on the right, and I have a length over time squared on the left. So dimensional analysis tells me that I haven't made a bad mistake. Okay, and then you start looking at it in a little bit more detail. You say, let's look at the sign. Okay, signs are super important. That's where a lot of your mistakes are, is with the signs, plus and minus sign. You look at this, that's positive and that's positive, so the acceleration is negative. Correct, sign is correct. Then you start thinking about it in a little bit more detail, and you say, well, this is really interesting. What this is telling me is that if I were to double the initial velocity of the aircraft, then VI, if I double that, squared, 2 squared is 4, then the required acceleration is negative, but it's 4 times the value. Doubling the initial velocity from this to this quadruples the magnitude of the acceleration, so the negative acceleration. 4 times the acceleration is required to bring it to rest. And basically, why is that? Well, you can see acceleration times L, it's constant acceleration, times distance. That's basically force times distance is work done, is energy. Energy is proportional to velocity squared. So you have some initial kinetic energy here, which is 1/2 mvi squared. You have to dissipate all of that kinetic energy, maybe it's through friction or whatever. You have to dissipate all of that kinetic energy. You have the same distance, so it requires 4 times the force. Work done, energy transferred is force times distance. So the force has to quadruple, so the acceleration has to quadruple. Double the initial velocity, you quadruple the energy. So the acceleration and forces involved need to quadruple as well. Makes sense. You want to think about your formulas like that, okay, and make sure that they make intuitive sense. Or you look at the L in the denominator. So if you were to take that same initial velocity and so on, if you were to double the length of the aircraft carrier, what it says is that the acceleration would be reduced, magnitude of acceleration would be reduced by a factor of 2. It would be only 1/2 the acceleration, which makes sense because you have longer to slow this thing down. And so the acceleration can be, the negative acceleration can be more gentle. And so the acceleration gets reduced. L is in the denominator. So when you've gone through an analysis like that of your answer, there's almost no way that you're wrong. So what I want to encourage you to do is get to the point where there's no uncertainty whatsoever whether you've got the answer right or wrong. It's right. Okay, great. And then, so we've solved for the unknown A. Then we can solve for the unknown delta t. Well, in fact, we have the answer right over here. Delta t is 2L divided by VI. So that's the second equation. Delta t, let's put it up here. Delta t is equal to, what did I say? 2L over VI. Okay, so L is known and VI is, we're assuming that L and VI are known, and we've solved for the second unknown. So let's put a square box around that. Okay, and then we look at that and we say, are we done? No. Now we need to think. Think like a physicist. Is this a reasonable answer? Think first about the dimensions. Okay, so on the left-hand side, the dimensions of the left-hand side are time. The dimensions on the right-hand side are a length divided by a velocity. That's a length over time. Length divided by length over time is time. Correct. Okay, so we haven't made a serious mistake. Okay, we got dimensions of left-hand side equals dimensions of right. The next thing to think about is, is this a reasonable sort of answer? So it's saying that if you were to double, keeping everything else the same, if you were to double the length of the aircraft carrier, it says that the time required to stop would be double. And that's right, because the acceleration would be reduced, okay, and then the time it's going to take to get from there all the way over to there is going to be longer than the time under higher deceleration to get from there to there. Okay, and so like your average velocities your accelerations are lower. Okay, so longer deck means longer time to come to rest. Also, you have an initial velocity in the denominator. If you were to double the initial speed from this speed to this speed of it coming in, well, then all the speeds are faster and it's going to take a shorter amount of time to come to rest. So you double VI in the denominator, you 1/2 the amount of time it takes to stop. Okay? So that all makes sense. And you can also think about this equation as, L, the aircraft carrier length, is equal to, according to this equation, L is equal to 1/2 VI delta t. And so you think about that and you say, well, I know that if the velocity were constant, then the length would be the velocity times time. Okay, but the velocity is not constant. The velocity starts at a value VI and then drops to 0. And so the length, the distance it can go, will not just be VI times delta t, because the velocity is always getting smaller. And so the length it can go is less than VI delta t. And in fact, it's exactly 1/2 VI delta t. It's basically the average velocity times that time. Okay, that's the displacement, delta L. So you know for certain that this answer is correct. You don't have to, be uncertain about it, right? So run through checks like that, signs, dimensional analysis, and double variables, and see whether the changes involved make sense. Great. And then the last step in a typical sort of physics problem is we're just trying to sort of think about the kinematics involved in an aircraft carrier landing on an aircraft carrier. Okay, and so I don't know what these VIs are. I don't know what any of these numbers are. Let's make some up. Okay, so let's see. We said that we knew these guys. Okay, V final is 0. We knew V initial and we knew the length of the aircraft carrier. So I don't know, do we? Well, let's just guess. Okay, so let's say V initial. How fast is that? I have no idea. I could look it up on Google, but what I'm going to do is I'm just going to think. I'm going to say, well, you drive about 100 kilometers per hour on the highway. These military jets would come in, faster than that. Maybe it's 150, maybe it's 200. Let's actually put in, just because I have the number 250 here. I've got it worked out. Let's just suppose that it's 250 kilometers per hour. Okay, so we're just sort of estimating that. Okay, just sort of based upon common sense. And then we realize, oh, wait a minute, we're using SI units, and so we can't have kilometers and hours, we need meters and seconds. So I'm assuming that you know how to convert, say, 250 kilometers per hour into meters per second. And the way you do it, just to remind you quickly, is you multiply by 1 in various forms. Okay, so suppose that you wanted to eliminate kilometers in favor of meters. So you'd have a kilometer down here, and you'd have a meter up here. So it turns out that, of course, 1,000 meters is the same as 1 kilometer. So 1,000 meters and 1 kilometer are the same thing. So when you divide them, you get 1. So this is just 1. So you haven't changed anything, except that you've changed the kilometers here cancel and you're left with meters. Similarly, you don't want hours in the denominator. What you want in the denominator is seconds. Okay, and you want hours in the numerator. Well, you know that 1 hour is 60 times 60 is 3,600 seconds. Okay, so then that'll cancel that unit of hours, and you're left with seconds. You have meters per second. Okay, and then you crank out those numbers, and what do you get? This is 69.4. In general, whenever you're solving any physics problem in 121, use maximum number of significant figures as 3 sig figs. Okay, any more sig figs is just usually ridiculous. Okay, completely unwarranted. You know things that accurately. Okay, and then the second thing we said is, well, let's estimate the size, the length of the landing strip on the aircraft carrier. So I don't know, how long is a ship like this? It's not a kilometer. It's not like 10 meters long. Maybe it's something sort of in between. Let's suppose that it's around 100 meters. Okay, ships would be longer than that, but the whole runway is not usually the entire length of the ship. So let's say it's 100 meters that the aircraft has to stop in. So then we have now numerical values for VI and for L, and we can plug them in. we can calculate the acceleration and the time. Let's calculate the acceleration first. So the acceleration is negative. Okay, it's VI squared. So VI is 69.4 meters per second, and we're going to square that. We're going to divide it by twice L, 2 times 100 meters. Okay, and so when you crank that out, you crank out the numbers. So what does that turn out to be? Negative 24.1, negative 24.1. You check the units. Always have units when you input numbers in. Okay, so meters squared per second squared divided by meters is meters per second squared, and that's indeed an acceleration. Okay, are you done? No. Okay, so 24.1 meters per second squared, is that big? Is that small? Who knows? So you need to, whenever you calculate an acceleration, compare it to an acceleration you're very familiar with. What's that? Well, free fall acceleration. An object free falls with an acceleration g equals 9.81 meters per second squared. So how many g's is this? Well, you go negative 24.1 meters per second squared. You're going to convert from meters per second squared into g's. Okay, and so you say, well, I want to eliminate meters per second squared. Okay, so I put that in the denominator. So I know that 9.81 meters per second squared is 1 g. Okay, and so then you go 24 over 9, and what do you get? You get about 2.5. That's about negative 2.5 g's. Okay, so, you know, when people talk about acceleration and deceleration in race cars and airplanes and so on, they measured in g's. Okay, and so this is about 2.5 g's. And so that's good. That's okay. I don't remember exactly the numbers, but something like 6 or 7 g's, you start to lose consciousness. So we don't want that happening. So good. Okay, so we're still in the safe zone there. But it's a lot. 2.5 g's is quite a bit. Okay, and then finally we say delta t. Let's solve for delta t. Delta t is 2L divided by VI, so it's twice the estimated length of 100 meters, okay, divided by the initial velocity. The initial velocity was 69.4 meters per second. Meters divided by meters per second is seconds, that's right. And the numerical value turns out to be 2.88 seconds. Okay. Then we say, again, is that a reasonable number? Well, I don't know. If you said, like, just imagine this. You have something about 100 meters in size. You have something coming in at about twice the speed of highway speed, and this thing is coming to rest at a constant rate. Okay, and so you could just imagine, here it comes in, 0, 1, 2, 3. You can imagine 3 seconds is about reasonable. 30 seconds would be too long. 0.3 seconds would be too short. So you're in the right ballpark. Okay, so make sure that you're just sort of in the right ballpark. And that's it. So here's a good example of a kinematics problem in one dimension for this course. And what you want to do is solve problems in general. Okay, and then and think about the problem in general with a good diagram, position, velocity, acceleration versus time graphs. Start with the two general, solving any kinematical problem, the foolproof way to do it is to start with the two general kinematical formulas, specialize them to constant acceleration, then start plugging in what you know. Okay, and lots of them are zero and so on, and then you end up with two equations. Then you solve those two equations for what you've decided the unknowns to be. Okay, and then estimate some numbers and plug them in and check whether that all makes sense. So this is like a full solution of a general sort of kinematics problem. Yeah? Okay, let me give another example. Okay, so this is a second example of a good kinematics problem in Phys 121, and that is sort of a catch-up type problem, where somebody is, say, moving with constant velocity and the other person is moving with constant acceleration. Okay, so the picture is something like this. So again, we're not interested in any sort of particular solution. We're interested in understanding catch-up problems in general. So the situation looks something like this. So we've got a roadway here, okay, which we'll take as, the x-axis, and we've got two people in motion. So we've got, let's start with Alice. So Alice at t equals 0, Alice is located some distance d along the road, and she's moving with constant velocity to the right. Okay, so here is Alice, and she's just walking along the road like this. And she's walking, so this is Alice, A, and she's walking along the road with a velocity of Alice is constant, and some positive constant value. She's just doing this. And her acceleration is 0. If her velocity is constant, her acceleration, so the acceleration of Alice is equal to 0, and her initial position is d. Okay? And when Alice reaches the point D, at that instant of time, Bob, who is located behind her like this, so Bob starts running. Okay? He starts at rest, and he starts to run with constant acceleration to catch up with Alice. Hey, Alice, wait up! And then he starts to run to catch up with her. Okay, so this is Bob. And we say, what do we know about him? So we're assuming v Bob initial is equal to 0. Bob's initial velocity is 0. And we'll assume that Bob runs with constant acceleration. So a Bob is some positive number, and it's constant. And again, we assume constant acceleration just for simplicity, so you won't have to use calculus, okay? So we have that. So this is the picture, at t equals 0. Okay, and then as time goes on, Alice continues to move at a constant speed. No matter how far Bob is back, no matter how big d is, and no matter how small his acceleration is, he will always, if he runs long enough with this constant acceleration, he will always catch up with Alice. And when he takes over Alice's position, Alice will be down the x-axis further, and Bob will catch up, and he will clearly be moving faster than Alice when he overtakes Alice. And you might be interested in things like, well, how much faster than Alice is he moving, and so on and so forth. Okay, so you might be interested in things like, how long does it take? What is the time interval required for Bob to catch up with Alice? Another thing you might be interested in is, how fast is Bob moving? So what is v Bob final when he overtakes Alice? V Bob final, as we said, is going to be greater than v Alice, but how much greater? You might also be interested in, the distance d here, say capital D, where these two guys meet each other. Okay, so let me just calling it d, let's say, x Bob final is equal to x Alice final. So x Alice initial is d, x Alice final is here. X Bob initial is 0, X Bob final is here, where they finally meet and Bob overtakes Alice. We might be interested in what is this distance from the origin. Okay, that sort of thing, right? And so we look at this and we say, well, there's lots of variables here. We have initial position, velocity, and the constant acceleration of Bob. We have initial position, velocity, and acceleration of Alice. And we've got only two kinematical formulas. However, there's two kinematical formulas describing Bob's motion and two kinematical formulas describing Alice's motion. So in fact, we have 4 kinematical formulas. Okay, and so Yeah, so let's just sort of analyze this thing and start to think about it, start to see what emerges. Okay, so the first thing you want to draw is a position versus time graph. And that position versus time graph will show Bob's position as a function of time and Alice's position as a function of time on the same graph. Okay, so here is the x-axis, people moving on the x-axis as time goes on. So let's start with Alice. Alice is easier. So at time t equals 0, this is time 0. At time t equals 0, Alice is located a distance d along the x-axis. And as time goes on, her distance d along the x-axis, her position along the x-axis increases linearly with time because her velocity is constant. So let's say, looks something like this. So it's a straight line. So this is a straight line whose slope is equal to the velocity of Alice, which is some positive constant number. Okay? And what else? So that's pretty much it. So this is x Alice initial is equal to d, and at some point they're going to catch up. So after some unknown amount of time delta t, we will have x, this will be x x Alice final, which we don't know. Okay, and that's it. And then the next is Bob. Okay, so Bob starts off at x equals 0. So at t equals 0, Bob is here. Okay? And Bob starts out with 0 initial velocity. If the initial velocity is 0, that means the initial slope of Bob's position versus time graph is going to be 0. So it starts off with 0 slope. So slope equals v Bob initial is equal to 0. So Bob starts off with 0 initial slope. He's undergoing constant acceleration, so his velocity increases linear with time. His position increases quadratically with time. So what we want to do is we want to draw a parabola. Okay, and that parabola has 0 slope here, and it increases like a parabola. And at time delta t, x Alice, x Bob final is equal to x Alice final. They meet at this unknown point. And so you draw a parabola that starts here and ends here, starting with 0 slope. You go up like this. So that's what a parabola looks like. And so this slope right here, that slope is, I should put it here, a little triangle here. This is v Bob final. Bob's final velocity will be the slope of his position versus time graph at that delta t, that final time. And that slope, v Bob final, is clearly bigger than the slope of Alice's position versus time, because Bob is going to overtake her moving a lot faster than she's moving. Okay, so we have that. And I think that's it. Oh, we should also put in here just x Bob initial is equal to 0. Okay, so we have x Bob initial, x Bob final, and we have constant acceleration. This is constant acceleration Bob is undergoing. Okay, and we have the initial velocity is 0, and the final velocity is some unknown VB final. Okay, so that takes care of both Alice and Bob, position versus time graphs. The crucial thing is they meet at this point. This is the crucial condition, okay, that connects these two curves, and that's what we need to really pay attention to. Okay, so now we say, yes, now how are we going to solve this problem? How are we going to proceed? Well, what we really want to do is we recognize that there are only two fundamental kinematical formulas, and so let's use the basic ones, which just come from the definitions of velocity and acceleration. Okay, so let's start down here so we don't run out of room. We've got equation number 1, the first kinematical formula. We're going to write that down for Alice. Okay, so the first kinematical formula says that the displacement is equal to the average velocity times the time interval, delta t. This is a general kinematical formula, valid for constant acceleration or non-constant acceleration. And then what we do is we specialize this to the case of constant acceleration. Okay, and so we're going to say, we're talking about Alice. Alice's acceleration is actually 0, and her average velocity is just her constant velocity that she's walking at, just VA. Okay, and so we say delta x for Alice, that's going to be x Alice final minus x Alice initial, okay, is equal to Alice's average velocity, well that's just her constant velocity that she's walking at, that's v Alice, times this unknown time interval, delta t. And then what else do we know? We know that x Alice initial is equal to d. Okay, so this variable here is equal to d. Okay, and then we can rewrite this equation, just sort of simplify it, rearrange it a little bit, and say x Alice final, this unknown, this crucial unknown, you're going to generate an equation for x Alice final, you're going to generate an equation for x Bob final, and you're going to equate those two, the crucial condition where they meet. So solve this for x Alice final, take the negative d to the right hand side, is equal to d plus v Alice delta t. Okay, so that makes sense. So when the time is 0, Alice is at position D, and then her position increases linearly with time at a certain rate, VA. Okay, so that's one of the equations. Let's call that equation A. Okay, and then let's write down the first kinematical equation for Bob. Okay, so the general kinematical formula is delta x is equal to v average delta t, applies in all circumstances. Then you specialize this equation to the case of Bob. So Bob is undergoing constant acceleration. If the acceleration is constant, then the average velocity is 1/2 initial plus final velocity. So we have x delta x for Bob is x Bob final minus x Bob initial. You set that equal to the Bob's average velocity. Well, what's that? Bob's average velocity is 1/2 v Bob initial plus v Bob final. Okay, Bob's velocity is increasing linearly with time. The average value is the initial plus the final divided by 2. Takes you halfway in between. Okay, that's the average velocity times delta t. And then we look at that and we start to specialize. Well, x Bob initially started at x equals 0, so that variable is 0 in this. V Bob initial, his initial slope of his position versus time graph was 0. He starts at rest. Okay, so V Bob initial is 0. And we don't know what V Bob final is. That's this slope over here, which is an interesting thing that we're going to solve for. Okay, so great. So then we rearrange this and we say, yes, x Bob final. Here's an expression for x Bob final. Let me just pause and get another marker. Okay, back with a fresh marker. All right, so we have x Bob final. Okay, we just solve for x Bob final. Well, that's equal to 1/2 v Bob final delta t. 1/2 v Bob final times delta t. Okay, and we'll call that equation B. This is a lot darker green. Okay, and then, yeah, great. And then the second thing we do is we write down the second kinematical formula, general kinematical formula, for both Alice and Bob. Okay, so starting with Alice, we have, following from the definition of acceleration, we have delta v is equal to a average delta t. Okay, and then we specialize to the case of constant acceleration, and in Alice's case, that constant acceleration is in fact 0. Okay, and so what this equation simply tells us is that delta v equals 0. So v Alice final minus v Alice initial is equal to 0. So v Alice final equals v Alice initial. And that's obvious because her velocity is constant. Both of these are equal to VA. VA minus VA is 0. So this equation really doesn't tell us anything. Okay, so there's no new information. Okay, and then we write down the delta V equation for Bob. Okay, and then this is general. We specialize it in the case of constant acceleration. So Bob's acceleration is constant, some unknown value AB. And so the left-hand side is delta V. So V Bob final minus V Bob initial. The change in Bob's velocity, that's this slope minus this slope of 0. That's equal to Bob's average acceleration. Okay, and that average acceleration is just Bob's constant acceleration AB. Okay, and we multiply that by the unknown time interval delta t. Okay, so now we've gotten to that point, and then we further specialize and say, do we know v bob initial? Yeah, v bob initial, the initial slope is 0, so that's 0. And so then the equation simplifies to just this guy. It says v bob final is equal to his constant acceleration times the time. Okay, so that's pretty clear. Bob starts with initial velocity 0. He accelerates at a constant rate for time delta t, and so then his final velocity is just his acceleration times the time interval. Okay, that's that velocity. So we'll call that equation number C. Okay, and then what should we do? And then we'll look at basically what we want to do, the key condition again. We have two curves here. One is a straight line, 0 acceleration. One is a parabolic line under constant acceleration. Okay, and the key piece of information that connects these two diagrams is where they meet. So we need to solve for x Alice final and x Bob final. Oh look, we've done that. And then equate that. So we want to equate these two things. And so x Alice final, on the left-hand side, we have d plus v Alice delta t. We have that is equal to v Bob final. 1/2 v Bob final delta t, is that right? Right, sorry. What we want to do is actually simplify this one a little bit. So we have equation B here. This is for sure an equation for x Bob final, but we have a v Bob final in there that we don't know. And so we're going to take v Bob final from this third equation and substitute into there. Right? So that's equal to 1/2 v Bob final is a Bob delta t. And then we multiply by another factor of delta t. Okay, so we have that equation. Okay, so this is the equation which says that they meet at the same point. Okay, and so in this equation, everything is known. We're assuming we know, say, the distance they start at, Alice's velocity and Bob's constant acceleration. And so then we can solve this equation for how long it takes Bob to catch up with Alice. Okay, and so this is a quadratic equation. So we'll rewrite that quadratic equation as 1/2 AB a Bob delta t squared minus VA delta t minus d is equal to 0. You recognize this as the quadratic formula. The solution to the quadratic formula is delta t is equal to negative this middle term. So that's VA, negative of negative VA is positive VA, plus or minus the square root of the middle term squared, VA squared, minus 4 times this times this. So that minus sign will cancel, become a plus. 4 times 1/2 is 2. So it's 2AB times D. And then you divide by twice the first term. Twice 1/2 AB is just AB. Okay? And so that tells you that the time, this is an important result, it tells you how long does it take under these circumstances for Bob to catch up with Alice. So it's this. Now I want you to pay attention. Whenever you have a quadratic formula, there's a plus and a minus sign, and you need to decide which one is correct. In this case, it's pretty easy to see. So this thing under the square root is a VA squared plus a positive number, which means that the value of this square root is larger. This square root is larger than VA. So if you go VA minus something larger than VA, your time interval will be negative. Well, that's not right. It's got to be a positive time. Okay, so then you take the positive solution. And so, yeah, we'll just leave it as that. But it's always very important and interesting to think about what the negative solution corresponds to whenever you have a quadratic. It's a really good exercise to do. So let's look at this picture here. What we've drawn so far is x. I'll just sort of sketch it sort of roughly. What we've got is an amount of time delta t here, and this is 0. And what we have is a quadratic function, which goes up like this. And we have a linear function, which goes like this. And they intersect at this point, delta t here. Okay? This is delta t. This is the solution where delta t is positive. Okay? There is also a solution where delta t is negative. What could that possibly correspond to? Well, if you look at how we've specified the problem, we didn't say anything about what happened before t is equal to 0. We said after t equals 0, Alice is moving with constant velocity to the right. Well, what if Alice is moving with constant velocity to the right also before 0, time 0? So then her position versus time graph would extend this way, before time 0. What about Bob? All we said about Bob is that t equals 0, his initial velocity was 0, and he was undergoing constant acceleration. So he would have a parabola like this. However, we didn't say anything about Bob before 0. We could say, well, suppose he had that constant acceleration even before 0. That means his path, his position versus time graph, would be a parabola that continues into the negative. What does this correspond to? That seems a little weird. Let's think about it for a second. What it's saying is that for large negative time, say back here, it's saying that that Alice was certainly like further back, and in fact here she's actually to the left of the origin. So at some large negative time she's to the left of the origin and just walk, walk, walk. Okay, but then Bob, it's saying that Bob was at a large positive x value and a large negative velocity. So remember, it's constant acceleration, so it's saying that he's moving with he's initially back here moving with a large negative velocity, and then there's always a constant acceleration to the right, slowing him down, slowing him down, slowing him down, slowing him down, until at this point he reaches momentarily 0 velocity, and then he starts to pick up speed faster and faster and faster. Okay, so he starts way to the right, comes whipping this way, and then he intersects Alice the first time here. Okay, and then Alice continues on. Then he's at rest, and then he starts to pick up and catches her. Okay, so it's important to, as a good exercise, to think about that differences in sign, you know, and different solutions. What you're trying to do as a physicist is you're trying to understand not particulars about any situation, but to understand a situation in as much generality as possible, and looking for the alternate solutions and trying to understand them is helpful. Okay, great. So that's the time interval, and what else can we say about this? That's basically it. And then the last thing we want to do is we want to figure out, say, what v bob final is. How fast is he moving when he catches up with Alice? So we have this equation, v bob final, equation C, is a bob times delta t. We figured out delta t. Multiply that by a bob, just cancels the a bob in front, and it says that v bob final is equal to v Alice plus the square root of v Alice squared plus 2 a bob times the distance d. Okay, so that's a second really interesting thing to know. Okay, so we can see that clearly Bob's final velocity when he catches up with Alice and overtakes her, is equal to Alice's velocity plus something that's even bigger than Alice's velocity. So v Bob final is actually somewhat bigger than twice v Alice. So that's an interesting thing to notice about this problem. Okay, and finally we might want to plug in some numbers here. Okay. So again, I don't know, we can just make up these numbers. Let's suppose that the distance d, Alice is, say, 20 meters down the road, okay, when Bob sees her walking with a constant velocity, say v Alice is, let's say, 1 or 2 meters per second. Let's say 2 meters per second. She's walking rather briskly. She's getting some exercise. And let's take Bob's acceleration. Now, this is a little bit of a tricky one because really, your acceleration, when a person starts at rest and starts running, their acceleration is large, okay, like at least a g, that kind of acceleration, right? If he had that acceleration, then he would be moving like super fast when he caught up to Alice, unrealistically fast. And so if you play around with the numbers a little bit, if you take a bob to be about 1/8 of a meter per second squared, which is much less than 1 g, okay, so it's a very, very gentle acceleration the whole time. Constant gentle acceleration, and then the numbers work out pretty reasonably. So then you can figure out delta t, plug those numbers into this formula, and you get that delta t is about 40 seconds. And so you can imagine, she starts 20 meters ahead, she's moving at 2 meters per second, and they finally catch each other after about 40 seconds. So that seems to make sense, roughly. And what else? V-bob final. So you work out V-bob final, plug everything in here, and what do you get? You get about 5 meters per second. Okay, so Alice is moving at 2 meters per second, and Bob's speed when he catches up is greater than twice, because remember, this thing is bigger than VA, so it's VA plus something bigger than VA. It should be more than twice, and twice 2 is 4. That's more than 4. Okay, so that's right, and that's right. Okay, so this is a great exercise, this kind of a catch-up problem, being able to sketch position versus time for both objects in motion. And again, always just write down the general formulas, the two general kinematical formulas for both objects in motion. Specialize to constant acceleration, plug in things that you know, and then start solving the equations, and then at the end estimate some numbers and plug in plug in those numbers and look at those answers. And along the way, check things out. Check if they make sense. Check if you haven't made a mistake. This is a great problem, so I really encourage you to think through a problem like this, sort of thinking like a physicist. It's a rich problem. This is what the solution to a physics problem looks like. All right, very good.